Hey, welcome to the lesson for Lecture 6 on Week 3 of the Geology of Nebraska, and this week we're focusing on sedimentary rocks and processes and also on sedimentary environments. So why exactly would sedimentary rocks be important? Well, first and foremost for our class, they make up a majority of the rocks in Nebraska, but they also inform us a lot about the Earth's history. They influence the development of our industry, society, and culture because we use them for building materials and energy and mineral reserves. And then, extremely important in the western half of our state, they're important sources of groundwater and groundwater reservoirs. So really, sedimentary rocks are quite important to us. Now, there's on the slide it says 3, but there are 4 different groups that we are going to be talking about of sedimentary rocks, and they're based on the way that they form. So we can have siliciclastic or clastic rocks, which are made up of weathered sediment grains that are cemented together, chemical rocks, which are precipitated rock from a supersaturated solution, carbonate rocks, which are made from calcium carbonate or calcite, and then organic rocks, which are made up of the buildup of organic material, like plants, and then transformed later on by heat and pressure into coal. So we're going to take each of these groups individually. So first we're going to look at siliciclastic or clastic rocks. So here's a slide just showing the formation of how these work. So we've got weathering and erosion of pre-existing rock into sediment, which is happening on the left-hand side of our image here. That sediment is then going to be transported by some sort of source of gravity through water, wind, etc. And then that's going to be deposited in a low-lying area, which is also known as a sedimentary basin. These sediments will build up over time, get buried and compacted together, and then through some chemical processes, eventually they get lithified and cemented to form the sedimentary rocks that we see across much of Nebraska. So yeah, in this image on the right, we can see the weathering process happening on land. It's being transported into our low-lying basin here, which is the sea. And then layers of sediment are building up. Plants and other matter are also going to be building up. That's where our fossils come from. And so we find a lot of fossils in clastic rocks. Clastic rocks are differentiated by a couple different characteristics. So we're looking at grain size, or the size of the actual grains in the rock itself, the shape of those grains, how well versus poorly sorted they are, and also the mineral composition. So there's a chart here on this slide that's pretty helpful for this. And also in the bottom left corner, this is a triangle that's used to determine the percentage of feldspar versus quartz versus rock fragments in a sandstone. So the closer you are to the source of where things are weathered, the larger the grain size is actually going to be. And when you have smaller grain sizes, it indicates deposition in a lower energy environment or very, very far away from the source of weathering. That's because as you move or get transported further, you're subject to more and more weathering, which reduces the size of your grains. So again, our rocks are classified this way for siliciclastic rocks. So when we have clay-sized grains, which are the smallest grain sizes, they're eventually going to produce mudstone, which is shown on the left, or also known as shale, which is shown on the right. You can see that you can get some laminations there, and you can get variations in color, but they are all made of clay-sized grains, so the same exact small size. Getting a little bit larger in grain size, you would produce siltstone. So this is slightly larger than clay-sized particles and produces a different rock type. There's also a distinct feature that are associated with glacial deposits known as loess, and that's wind-blown silt, which is on the right-hand image there. Going again, increasing grain sizes, we move to sand-sized grains. And so sand-sized grains are the type of grains that you might see on a beach or in a dune environment. And so this is just 2 pictures here. We have feldspathic sandstone on the left and quartz sandstone, which is a little bit lighter colored on the right. Now, grain shape is also helpful when identifying rocks. So grain shape refers to whether the clasts are angular or rounded. Angular grains would again indicate deposition closer to the source because they haven't been subject to weathering or erosion for very long, whereas rounded grains would indicate more transport. So there's 2 types of rocks that this is differentiated between. So breccias are larger angular grains. They're poorly sorted, and they have gravel to clay size grains there. Conglomerates have the same grain size, the same poor sorting, but their grains are rounded, so that indicates that they've had more transport. Grain sorting can also tell us about whether the energy of the environment was constant or variable. So when there's a well-sorted rock where the grains are all the same size, this indicates a uniform energy. Hence a beach environment where we're getting wave action regularly. When it's poorly sorted, this indicates variable energy. So an example of this will be an alluvial fan, which we'll talk about more in the next lesson. Class composition is also important here, so we can have, again, this alluvial fan has a lot of different compositions in there, but as you get to a beach, when there's more transport, you get grain sorting of different actual types of grains there. So their quartz is very resistant to weathering, so in beach environments where there's been a lot of transport and weathering, you get a lot of individual quartz grains. All right, so our second type of sedimentary rock are chemical rocks. Chemical rocks form in some different ways, but overall they really form from the precipitation of a rock from a supersaturated solution. So think of salt water here. This is imaged on the right. So say we have a really, really salty, watery basin and high evaporation rates. As the water evaporates, that solution becomes supersaturated in salts. They crystallize and they get deposited at the bottom of that basin. And then over time, you get gypsum or halite forming. You can also have chemical sedimentary rocks form in other ways. So travertine is a type of calcium carbonate precipitated from groundwater where it reaches the surface. And dolostone is a modified carbonate from magnesium-rich fluids. Now the last type that we're going to talk about is the carbonate. And so calcium carbonate is a very, very diverse group of rocks that are typically associated with environments from between 30 north and 30 south latitude. So this area indicated by our green box. So when we see carbonate rocks, we typically associate those with tropical, shallow, warm water environments. Carbonate rocks typically form after organisms with calcium carbonate skeletons die. Their remains build up on the seafloor, building a limestone deposit with shells and shell fragments, and then are cemented together with calcium carbonate that's precipitated between the grains. Sounds complicated, but really it's a bunch of things die, get compressed together, and eventually form these rocks that you're seeing below. So when there are large visible fossil pieces, indicated on the left-hand side, this turns into what's called fossiliferous or skeletal limestone. But when there are microscopic plants and animals that have calcium carbonate skeletons and they die, like the image pictured in the middle right, these form finer grained carbonate rocks. So chalk, what we use on chalkboards and what's pictured here at the cliffs of Dover, forms from microscopic plants and animals with calcium carbonate shells as well. Then our final group is organic rocks. And so organic rocks are formed from organic material, such as decaying plants, and then it accumulates over time. So we can see that in the bottom figure on the left, we have a swamp where there's continuous deposition of decaying plant material, and then over time it builds up, putting pressure on the layers below, and so eventually this forms coal. It indicates a depositional environment, which we'll talk about again more in the next lesson, that it was swampy or plant-rich. So eventually it forms coal and what's pictured on the right there. So finally today we're going to take a look at the sedimentary structures that you can find in these different rocks. So sedimentary structures provide key information about the conditions under which the sediment was transported or deposited. The most important sedimentary structures are listed below, and we're going to go through these each in turn and look at some examples. So the first of these is stratification. So rock layers are typically known as strata, and stratification refers to the distinct layers that are expressed by changes in color, texture, and the way they weather and erode. So these layers, again, as I just stated, are called strata or beds. And that's pictured here in the bottom, so we can see that these different color bands would be different layers of strata or individual stratification. A second sedimentary structure that we look for are ripple marks. So ripple marks were deposited in water or windy environment, usually shallow with wave or currents. And so you can get two different types of ripples actually depending on the direction of the waves and currents. So asymmetric ripples form when there's one single current direction. So these are associated with rivers, with large dunes, whereas symmetric ripples are a back and forth current. So these would be associated with beach type of deposits. So we can see how both of those work on the right-hand side. The top is showing asymmetric ripples, where we have our sediment pushing up the shallow slope, then being cascaded over the crest to the trough on the steeper slope. And so that indicates one direction. And then the bottom is our symmetric ripples, indicating a back and forth motion where we have two equally sided slopes there. And that's how it would be shown in the sedimentary record in our bottom left image. Cross-bedding is typically associated with these ripple marks, so this is how it would express itself in cross-section or side view. So it's a type of stratification where layers within a bed are inclined at an angle to the upper and lower surfaces of the bed. They're formed by water or wind currents. So again, here's this process where we have wind carrying sediment up the shallower side of the slope. It cascades over the crest and then goes down the steeper slope into the trough. And this actually causes migration of dunes and ripples and rivers. So we get this formation of this distinctive cross-bedded layers. Graded bedding is just another type of bedding, so changes in strata. It's a progressive decrease in grain size upward through a bed. This generally happens over less than a meter thick, and it's mostly produced by turbidity currents on continental slope environments, which we'll see more of next lesson. There's also a video link here that I'll put in the lesson itself so that you can see what a turbidity current actually looks like. Mud cracks are a type of sedimentary structure that form when sediment dries while temporarily exposed to the air. So you can see how those are exposed in the sedimentary record as well as in modern environments on the left and right-hand side, respectively. So these form in areas that could be ephemeral lakes that are periodically dried or even tidal areas. And then finally our fossils. So it sounds like a lot of you are interested in fossils this semester. This is one of my favorite subjects. So for today, we're just going to talk briefly, but as we go through our field trips, our virtual field trips this semester, you'll get to take a lot closer look at these fossils. So the first thing to really note is that there's two different types of fossils that we can look at. There are body fossils, which are part of the actual body of the organism. So this includes skeletons, shells, leaves, branches, so the actual body of the organism. Whereas a trace fossil is evidence of life such as a trackway, a burrow, among other things. So they can tell us a lot about the environment that deposited the sediment they're in, can tell us whether things are marine or terrestrial, the type of temperature that the water was or the air was, the salinity of the water, the depth of the water, and so much more. So on the right-hand side, the top is an ammonite, which lived in the Cretaceous, and these ammonites are body fossils. And then the bottom is a dinosaur trackway.